All right, so this video is continuing the hypothesis testing, looking at one sample tests. So we are looking at inferential statistics still. We are still in the differences testing, and we are starting with Z and T tests. So this lecture is all about comparing our sample and the population. So we want to see, is there a difference in the way our sample is working and the population at large? And remember, population is defined however we want it to be. It's not necessarily every person in the United States or every person in the world. So for this, we're going to use either a one sample Z or a one sample T test. Those are our two choices. So here's an example of what we're trying to do. So we want to see if our intervention with a sample of 30 people made a difference compared to the population. So if I take if I can do a reading intervention for a classroom of 30 students, and I'm trying to improve their scores, then I can test if those 30 students are doing better than the population of the school. So I'm going to compare my sample of my classroom compared to the school as the population. If I was doing a medical intervention on college students, and I'm trying to decrease anxiety, so I could do, I could look at anxiety scores across a campus. That could be my population. And I do a medical intervention on anxiety. And I want to see if that decreased my sample compared to campus scores. Same with advertising. So if I do a huge advertising campaign to try to increase internet sales, let's say I really hit Colorado, and so I'm really trying to increase internet sales in Colorado, and then I'm comparing how is Colorado doing to the population of the United States. So if we know mu and we know sigma, that's going to be our choice, then we are going to use a one sample Z test. So here's the logic behind what's happening. So if I think homeschool students are going to score higher on their exams than traditional students across Colorado, then I'm going to state my null hypothesis. So the population mean of Colorado is equal to the the sample mean of my homeschool. So my two groups are homeschool and the population of Colorado. So my null hypothesis is saying that the two groups are equal. There's no difference between the two groups. The alternative hypothesis, I have three choices. I can make it non-directional, meaning I just want to know, is homeschool different than the population? I don't care if they're higher or lower. I could say that homeschool is higher, and I can say homeschool is lower. So I could make it directional. And in this case, I do care who's higher. So it goes back to the research idea and what they think. So in this case, we said the word higher. So it's going to be directional. So we write our null hypothesis and we write all alternative or research hypotheses. And then we have to decide what test are we going to use. In this case, we're going to use Z because that's what I'm telling you. We're going to calculate a value for Z. In just a moment, I'll show you that. We're going to change that to a probability value. So we're going to change that to a p-value. And we're going to compare that to our alpha. That will help us know, is the null true or not? So if our probability value, if our p-value is larger than our alpha, so if our alpha is 0.05 and our p-value is higher than that, then there is a high probability that the null hypothesis is true, meaning we are going to fail to reject it because it's probably true. If it falls on the tails, remember that one tail, two tail idea? Then we are going to reject the null hypothesis because there's a low chance of the null hypothesis being true. So we reject the null in support of our alternative that says that there is a difference. All right, so this one sample Z test. In summary, we are looking at if the sample differs from the population. And we know the population mean, and we know the population variance. That's huge, is the variance. Here's what the equation looks like. So we have our sample mean minus our population mean divided by standard error. Easy. We know all that. All you do is plug it in, divide it, and we're done. We get a z-test. So if we have a sample mean of 50, population mean of 60, and a standard error of the mean is 10, then we're going to say 50 minus 60 divided by 10, and we get a z-value of -1. So all I did was plug in the numbers, and I have a z-value of -1. I don't know if this is significant or not yet. So I'm going to change my z value to a p value. I'm going to go to Google, and I'm literally going to type in z to p value. I have a lot of different options. I like easy calculation because it does a lot of different things and it looks the same for all of them. So we're going to click on this one. And I'm going to type in my z-score of -1 and calculate. And I have some options. This would be my p-value for my alternative hypothesis. Because it was directional, I have to take into account if it's at 1 or 2. If we look at each one of these p-values, in this case, it doesn't really matter because all of them are greater than 0.05. So our alpha is 0.05. If it is larger than my alpha, then there is a high probability of the null is true, and I'm going to fail to reject it. So what's happening is our probability value right now is above 0.05. So we're falling in this dark gray range. So there's a high probability the null is true. We are going to fail to reject that, meaning it doesn't matter, meaning the sample mean and the population mean are essentially the same. There's no difference between the two. So you try with this one. Don't forget that standard error is the standard deviation divided by the square root of n. So take a minute and calculate z. So in this case, we get a very large z of about 22.7. So we have to decide is it significant or not. So I'm going to go back to my calculator and I'm going to put in 22.7. It is telling me that it cannot find a value. So the z must be between 6 and -6 because the tail in this case, our value is so far over here that it's essentially 0, meaning we have a very significant value. So the z-score here is significant, so I'm going to reject the null and say that there is a significant difference between sample mean and population mean. If we don't know the population standard deviation, then we are going to use a one sample t-test. And here's what it looks like. Almost the same. So we still have the sample mean, we still have the population mean, but instead of sigma, we are using S. So instead of the population standard deviation, we're going to have to sub in the sample standard deviation. And we do it the exact same way. So in this case, we have standard deviation divided by the square root of n. That gives us our standard error. And we plug in 63 minus 60 divided by 0.8485. So let's take a minute and do that in our calculators. And we get a t-value of 3.53, roughly. Again, we don't know if this is significant or not. So we have this t-value of 3.53. And we need to see, is it significant? So I'm going to go back to Google. And I'm going to type in t to p value. Again, it's not starting to work. T to p value calculator. There we go. We are going to scroll down. We have all kinds of different choices. So crazy. You can use any of them. It all does the same thing. This one is asking for our t value, and it's asking for degrees freedom. So degrees freedom I'll talk about in just a minute, but that is n minus 1. So in our case, 50 minus 1. Our degrees freedom is 49. Our significance level is 0.05. This we'll say is two-tailed. And it says our p-value is 0.0009. This is much lower than 0.05, and the result is significant. So in this case, we would say there is a significant difference, and the sample mean is different than the population mean. So I reject the null. Just a quick note, the difference between z and t. Equations are the exact same. It just depends on if we have sigma or if we have s. We always want to use sigma if we have it. So the information needed is the exact same. It's just this standard deviation that changes. So if we have population information, we always want to use it. The t distribution is a little bit different than z. So for low samples, so a sample of 30, let's say, we have a fatter tail and we have a shorter peak for the t distribution. And t changes as we get closer and closer and closer to the normal distribution. So as we get larger and larger samples, our distribution is going to follow the z distribution or the normal distribution. But for lower samples, it's a fatter tail and a shorter peak, which is why we underestimate. So since we are using sample information to try to predict and understand population information, we underestimate, and that's where this degrees of freedom comes in. So every time we substitute a sample statistic for a population, meaning we use S instead of sigma, then I'm going to underestimate and I lose 1 degree of freedom. So this just helps us because we are using sample information instead of population information to kind of underestimate our information that we get and our results. So think about this, take a minute and reflect on the difference between T and Z and when do you use each.